Today's experiment is going to be about finding the numerical aperture of an optical fiber. So, numerical aperture refers to the light gathering capacity of an optical fiber. We'll discuss what an optical fiber is. So, numerical aperture is given by, it varies based on this thing called the acceptance angle. The acceptance angle determines the size of, imagine the light falling on a surface to be a cone of light coming from a source. So the acceptance angle gives the size of that cone, and it can be guided through the optical fiber. So acceptance angle is given by theta A is equal to tan inverse d by 2z. We'll discuss what d and 2z are. So, speaking of optical fibers are basically this medium through which light or information can be uh, transferred. So, it's the best communication channel that our modern society currently has. It's made up of materials like glass or plastic, transparent materials basically, and it consists of a core and a cladding. So core is made up of a material which is optically denser than the cladding. So cladding is the outer covering of the core, and it will always have a lower refractive index. This is because optical fibers follow this principle called total internal reflection. So total internal reflection is seen when light that is coming from a denser medium, which is the core here, to a rarer medium, which is the cladding. Then if the angle of incidence reaches a certain critical angle, then the light will not refract outside, but it will reflect back into the core. So because of this, the light keeps on bouncing back into the core and traveling forward as it comes back. The angle which measures the size of the cone of light, like I said, it's given by tan inverse d by 2z. So here d is a quantity called the radius of far field intensity. What that means is that d is the distance from the point corresponding to maximum current. You'll see where that comes in. Maximum intensity of light is equal to maximum current, and from that point to the point which has 5% of intensity. So this you can calculate from plotting the graph. I'll explain it again. And so theta is equal to tan inverse d by 2z. So here z is the distance between the detector and the optical fiber, which we will also be finding. So using the value of theta, you can find the numerical aperture, which is equal to sine theta. So that is the experimental numerical aperture. You can also find the theoretical numerical aperture by taking the square root of refractive index of core minus refractive index of cladding. The square of both of these, the difference between the square of both of these gives the theoretical numerical aperture. So you can compare the two to see how much of an error you're getting. So the experiment starts by finding the least count of the micrometer. So all of these three, so micrometer works like screw gauge itself. So these three screws are the micrometer. So this is for moving the optical fiber in and out. This is for moving it up and down, and the one over here, which is what we're going to use, is for moving it from left to right. So the reason we're moving it from left to right is to detect how much current is, you know, so it detects the light gathering capacity of the optical fiber. So when the angle is changed, the angle between the detector and the optical fiber, it varies the amount of current that you can detect. So that will change when you move the optical fiber from side to side. So for a micrometer, you have, so this is the main scale or the pitch scale, and this is the head scale or the circular scale, same as the screw gauge. And to find the least count, so basically so when you move 1 mm on the pitch scale, you undergo 2 rotations. So the pitch is 0.5 mm, and then the least count, as you know, will be 0.5 by 50 because there's 50 divisions on the head scale, and that gives you 0.01 mm. It's the same as a screw gauge. So using that, you have to determine the distance between the detector and the fiber output in. So okay, so now for taking the readings, it should look like this. You start by moving the micrometer. I've already done it, but you start by moving the micrometer until the detector output is 0. So this will be your starting point on one end, and so it's about 12 on the main scale, as you can see. So note that down like this. You can take the readings the way you would take readings for a screw gauge, like I said. So you note down the total reading for 0 milliamps. So the output detects in milliamps, and then you start slowly rotating the micrometer. So you start rotating the micrometer until it goes to point 0.1. So for point 0.1, you note down the reading. So this is just initially you have to go from 0 to point 0.1 to point 0.2, and after that you have to start varying by point 0.2 difference. So because 0 and point 0.1 are very important, you have to note that down. So starting from point 0.2, you can note down for every point 0.2 difference in the current. So each time you note down the readings and then proceed to twist the screw again. So now you directly go to point 0.4, and it should be about, depends on the apparatus, and each time you note down the pitch scale reading and the head scale reading, and then find the total reading and repeat this until, so before you start this step you have to find out the value of the maximum output that your device can get, and keep that in mind. And once it reaches that, so for this apparatus it is 1.9. So once you reach 1.9, you note that down. When I was doing this experiment, it was 2.4, but for this apparatus, it's 1.9. So you have 2.4 here, but here it's 1.9. And once it reaches 1.9 and you note that down, you will notice that, okay, 2.0. So when I checked before, it was 1.9, but here it's 2.0. It doesn't matter. So as soon as you reach the highest, yeah, so 2.0 was the highest. So once you reach that number, you note that down and then continue the same thing. Don't change anything, and start noting it down for decreasing values of A, milliamps of I, of the current. So you had 2.4 and then 2.2, as you can see. So it went from 2.0, 2.2, 2.4 back to 2.2. So in the same way, for this device, it would work like 1.8, 1.9 again, 1.8. So now you note this down, and again continue the same thing for decreasing values of the current. 1.6, 1.4. Yeah, and continue doing that until it goes back to 0. So when you reach point 2, once again, yeah, once again note point 0.1 as well. So point 0.2, point 0.1, 0. Note all of these values down, and that completes the tabular column. For the plotting of the graph, you have to plot a graph with the x-axis for the detector output, that is the current that you recorded in milliamperes, and on the y-axis you will have micrometer reading, which is in millimeters. So once you plot the graph, it should have this kind of shape, and using, you will have to mark the peak value of the current output, and you will also have to draw a dotted line which corresponds to 5% of the maximum. So whatever the maximum current output was in my graph, you can see it's 2.4 milliamperes. So 5% of that will be at, you can see the dotted line, and from that point to the maximum intensity point you'll have to draw a line. The distance between these two will give you the value of capital D. Using the value of capital D from the graph and the value of Z, which we found earlier, you can find theta A, which is given by the formula that's written here. And once you find theta A, you can find experimental numerical aperture, which is somewhere around 0.752 for me. And the theoretical numerical aperture can be calculated using this formula. And that's the experiment. You will get these two values, and as long as they're somewhat close to each other, of course the experimental numerical aperture will be slightly higher or lower because the apparatus isn't perfect, but that's the experiment. So those are the two things you'll have to find.